So let me first thank Chairman Ma. Invited me here to introduce some nano-function materials and its industrial applications. So my name is Weijia, from physics department, but basically in our department, all professors are doing some fundamental research. But however, some of them still carry out for some applications like materials. So let me first, topic actually is introduce advanced function materials and its applications. So in this talk, I'm introduced to 3 types of materials, but all these materials are based on the nanoparticles. So first one, I'm introducing electro-rheological fluid. So we call it ER fluid, so which is a very famous fluid in our university. The next one, I'm introduced to the smart polymers, so which can be used in some smart window, smart roof, and smart display. The next one is a smart drug, so which is very useful for cancer treatment, or drug delivery. We call it smart drug delivery. So let me first introduce what's a ER fluid. So actually it's a basic fluid. So you can say there's some nanoparticles. So this nanoparticle, just like a powder, it just mix with liquid. So what's liquid? This liquid is a non-conducting liquid. So it's mixing together. It's like a yogurt, like a yogurt. It's a very, very low viscosity. But however, this material is very, very smart. When this material is applied to the electric field, that means you apply the voltage. It's changing from liquid state to a solid. So this change can be reversible. So we call it a smart materials. Also, we call it solid-like materials. It's not real solid material. It's a solid-like. So this transition is very fast. Its response time is 1 millisecond. So very, very fast. So it's reversible. So here is a conventional ER fluid. So here's a particle. So you just fabricate the nanoparticles like a powder, and then mix with silicon oil. Then silicon oil, and oil is a non-conducting. So you just mix together and then mix and just mirroring. So you can like this. So this is a ER fluid. So this ER fluid is like a yogurt, like a milk. It's a very viscous, very low viscosity. So how to calculate ER strength or ER effect? That means it's hardness of these materials. So let me show you here how to measure it. So here is a sandwich. ER fluid is sandwich between 2 discs. So you just pull this upper disc. So you can say the ER fluid can be broken. So we can measure this broken property of the materials and know its Youngster modulus or hardness of these materials. So you can see here, without application of electric field, that means no field, no voltage applied. So you can say its appearance like an oil. Its viscosity very low, like a water. But however, if I apply a little bit electric field, that means 1 kilovolt per millimeter. Like you can use a transformer, and you can use a battery, like this battery, and you can transform to a high voltage. But no current, remember, no current. So you can say it's become doufu. So his hardness become doufu. But however, if you further increase electric field, it's become hard form. And you even very high electric field, his hardness looks like a plastic. So this transition very fast. Just apply electric field. This change from liquid to solid is very, very fast. So what's application for these materials? So you can think about these materials applications. So how does it work? Actually, it's very simple. Principle is very simple. But from 1995, our university started to this investment of these materials. So almost 20 years. How does it work? So this working principle is very simple. You can see here, there are 2 particles just suspend in oil and apply electric field. So this particle will be polarized. Polarized means here's the positive and negative charge goes to the 2n. And here you can see positive and negative can be attractive, like a magnet. N and S attract each other. So this attraction force is proportional to applied electric field. That means it applied to the electric voltage. So you can change the voltage, you can change the force between the particles. Okay, so how about this? So all the particles suspended in the oil, it's just randomly. But however, apply electric field. So all these particles will align along the electric field directions. So this is electric directions. That means it's here, tail, connection. So this is a chain. So this is a chain. We call it chain formation of the particles. That means it has some structure change of the materials. Okay, so all these chains surround in the liquid. What's going on for this? So if we further increase electric field, that means you apply high voltage, right? These chains aggregate to form columns. So you can see here, this chain form columns. Okay, so this can be changed from random part to the columns. The chain is, here you can see how to know this strings. Let me show you. This electron, that means sandwich between the ER flow, is the columns. If you share one of electron, like this, you share, right? You cannot move. Why? Because this ER column bound to electron. So it's very difficult to share one of the electron. But however, if you increase the force, this can be shared. So from here we know high electric field is very difficult to share. That means we say it's very difficult to break the bond chains. So this is the ER effect. So from here you might understand what's the electric effect, what's the hardness of electric field. That means structure change of particle induce the strength of the hardness of the ER flow. So it's a principle. It's a very simple principle. So from here, the different electric field, the shear stress is increased difference. That means the hardness of ER flow responds to the electric field strength. So you can control electric field. You can change the hardness of these materials. So very useful for such materials in the industry. But that means this response time very fast. So you can see here. So what's our achievement for this ER flow? But actually, ER flow discovered 6 years ago by U.S. scientists, physics department guys, 6 years ago. But actually, this effect is not used in the industry. Why? That's because the commercialized ER effect is very low hardness. So it's very low. How low? That means you can change from liquid or from water to the yogurt. So its hardness change, but it's not strong enough. So it's not useful for industry. But however, a few years ago, the General Motors guys predict if this ER flow, if you want to use ER flow in industry for engineering, like a brake, clutch, damper. So you have 2 high ER stress. The ER stress is like, this ER stress must be like 3 kilopascal. But commercial one, its highest one is 5 kilopascal. It's much lower than the requirement of industrial applications. But however, our university, two professors, Professor Sun and I, discovered a new particles. This is nanoparticles in 5 years ago. At that time, they found another ER flow. We call it Young electric flow. So this word is very important. It's a Young electric ER effect. So our ER effect is much higher strain ER stress compared to commercial ones. This one is almost, but right now our ER flow is more than this. It's a first generation ER flow, but right now it's 200 kilopascal. So it's much higher in commercial one. So use these materials, we try to explain how to use the materials. So you can see here, it's a channel. Suppose it's a channel. And this channel, we just insert the electron in the channel. And then if ER flow can go through this channel freely. Why? Because no electric field. That's because no electric field, the ER flow like water, easy to pass. But however, if I apply electric field, so you can see here, it's apply high electric field. So the ER flow cannot pass this channel. Why? Because this region becomes solid. So we call this a electrical wow, or you can electrical damping actually. So it's a ER flow principle. And okay, so let me show you how to do this. So ER flow actually is very useful for clutch, a brake, and damping. So you can see here, you can use the train and the car or even a bicycle damping. So for all this can be used in ER flow, and eventually we want to replace our gears. Gears, you have to use a smart materials like a ER flow. It's very, very useful. Also, we have show you a demonstration here. So here's the ER flow sandwich between the two discs, and another one is rotate. The upper one is held by the 4 kilogram of weight. And if this ER flow can couple together, so this weight can be up. So that means you can demonstrate the ER effect. So here you can see the ER flow is the upper disc, lower disc, and here you can see it's a applied electric field is a 4 kilogram. It's lift up. So that means ER flow can easily like a clutch. So you can apply electric field, it's become coupled. So if you release electric field, it's become decoupled. So decouple depends on your field applied or without or with. So if you turn off electric field, it just fall down. That's because decouple. Yeah, here. It's up. Yeah, it's turn on electric field, it's decoupled. So it's a clutch. So it's a demonstrated clutch. But we have developed some clutch like this. So it just clutch, and here's a brake, just like an electric brake. Also, we can damper. So here's a damper. Yeah, here's a demonstration of this dampers. Yeah. So let me show you how that works. So here's the battery. Can see the battery is a very it's a 9 volt and a small transformer, and here's a 2 piston. You put this piston, you can use it. Put this, you can use it. But however, if I apply electric field, you cannot push. And so later you can try this device. This is demonstrate the damping or clutch system. This is our. Okay, so this is first introduction. A lot of examples. So ER flow is very useful not only for industry, but however he can use it in the bio system. So here we have developed a micro pump. Micro pump is a very small one. Micro pump and a micro mixer, micro PCR, and a micro droplet. This is an ER gate. ER gate looks like an electronic gate. So here's ER PCR. The PCR is very useful for the biomedicine or detection of the DNA. So it's a ER chips, use a ER flow. Okay, next one. I'm still saying smart polymers. So what's smart polymers? So here's a demonstration of smart windows. So this window, you have to use such a device like this. So here's you can see here's a window. It's 2 panels. So it's no electric field, no voltage applied. So you can see it's a light can transmit. So you can say it's women. But however, if you apply electric field in a left panel, so it's black. So that means you can change the transparent to the dark. So that means we call it smart window. So the smart window is usually a smart window is a liquid crystal. Liquid crystal is very expensive. The process is it's pretty low. It's difficult. So if the mass product maybe is for this building costs a lot. So it's not useful for the huge applications. But however, our invention is pretty simple. Its cost like a water, almost no price, like a water. So you just inject water, it's become. So it's we call it core polymer. So this kind of polymer actually can be aggregated with increase of the temperature. So we call this materials the temperature dependent materials. So you can see here. So it's low temperature, it's low particles. That means it's polymer is a three polymers. So and it increase temperature, it's become small particles. So if this particle size is comparable with the light, so you can see some scattering. So that's why it's become optical. So from here you can see, I'll give you examples. So here's a container inside with some small polymers. If low temperature, so this can use small particles. So its beam can pass this. We call it transparency. But however, if the particle is big enough, it's comparable to the light wavelength. So you can say this has some scattering. So its light can be broad. So let me show you later how does it work in our demos here. So how to use these materials? That's very simple. So suppose you know this glass. It's a green roof house. It's not glass. Some green house we use a glass roof house. So it's a roof is a glass. But however, in summer, it's some problem. Why? Because it's hot. So its temperature increase is its room is temperature rise a lot. So it's very hot. It's not useful for these guys. But in the winter it's fine. But in summer it's terrible. But however, if you use our smart polymer inject in the glass, so it's a change totally. So you can see here is a glass roof. It's a smart polymers. And the sun goes in, and inside the temperature increase, and this smart become black. That means if I apply the sun, totally reflect. So the inside temperature you keep a certain value. That means you can keep the room temperature. And if in the night it's become low temperature, it's become bright again, transmission again. So this materials is what we call use the smart materials. And here's a transition. That means you can tune the temperature. That means you can use temperature you can change. So with different applications, you can tune the temperature. You just change the additives of the polymers inside. So here's a show. This low temperature is transparent. It's like a water, and high temperature is become opaque. So you can see it's a different change. And here's a demonstration. So you can this materials you can apply the voltage. So this is like this. It's a smart window. So you can apply the voltage, and then later you can see in the center it's become black, become white. Why? Because it's change from small particle and big particles. So this is a phase transition. And the high temperature, let's say, is a block or it's a window. So we can fog windows sometimes. Another one we introduce the smart drugs. Smart drug is very useful for the drug delivery or smart drug release. So what's a smart drug? So smart drug is a core-share microsphere. So core-share like a chocolate. Yeah. Inside is a large, on the core is a chocolate. So it's a core-share. But the size is a micron. How small? Like here. So very small size. So it's very difficult to make such small size core-share materials or core-share sphere. But however, in our invention, we use a microfluidic applications. So this process can be mass product or microsphere. So you can see here, when we use this process, you can make particles like this. What's particle like this? It's a co-shear. Okay. So this co-shear structures. So in the core is a liquid. So we can use a drug. We use an aspirin solution as a core. The shear actually is a cross-link shear. It's a solid. And in the core, we adapted or mixed with nanomagnetic particles. Magnetic particle mixed with a shear is become magnetic shear. The inside is a drug, and there's some pores of the shear. So this side is very uniform. So this process is very useful for the drug release. So let me show you how that works. So it's easy to target. Why? Because suppose you have tumor in your stomach. So if you guide your particle with a magnetic field, and then you just use a magnetic field to stop this drug, and then you apply injection magnetic field, you can release purposely. So this is another one we call drug release. So you can use a magnetic field to control the drug release time, and also this material is biocompatible. So you can store in low problems. So it's biocompatible. So no any harmful for your health. And here you can see, you can control this sphere with a magnetic field, rotate, and even you can guide these particles. So that means this material, this particle, you can guide with a magnetic field. So we can with this magnetic field guide magnetic field guided microspheres. And here you can see. So here shows this without application of magnetic field. So this is spherical. However, if I apply magnetic field, so it's become, it's a expansion in one direction along the electric field. So if I apply the AC electric field, it's like a pump. It's like a pump. So this drug can be released from inside to outside through this core. So we call it a small drug release. So here's a property. So you can say how to control the drug release. Two conditions. You can control the magnetic field. That means you can increase magnetic field. Next one, you can control the vibration frequency. So you can control the electric frequency. You can control the release time. From this, we show you how does this work. Suppose here's a drug, here's a magnetic drug, and this you can guide with a magnetic field and go to the target. So this target is stomach. So you can stop this drug, small drug with a magnet, and then suppose here's a tumor here and some drugs inside, and just apply magnetic field. So this drug release can treat the tumors or cancers. But however, it's difficult to treat the blood. That's because there's some problems with size. But however, the stomach is easy. Okay, so let me conclusion for three types of materials. One is an ER fluid. So its applications, engineering. So we can use a damper, clutch, and you can use a digital fluidics, use a logic. So actually we have some patents with logic or fluid control, or you can use a bio-microsystem. You can use a micro mixer, like a pump. So we have a patent. Yeah, we have 5 patents, US patent, with different device patent and the materials patent. And next one is smart polymers. So what applications? Applications is a smart window, smart roof, and also you can construct a private room, a conference, and then you can bathroom. That's because some hotel is a window, is a bathroom, use a glass. But you have to close your bathroom, otherwise some guys will watch you, right? That's problems. But however, you can change your bathroom windows. You just turn on your electric field or voltage. And then you can make a large panel display. This is very important. Why? Because liquid crystal display is very expensive, huge panel. But this guy is very cheap, like a water. So don't care about its price, but you just design how to make this works. The next one, last one, is a smart drug. So this material is very useful for the smart drug delivery. And you can use engineering. Why? Because some U.S. company, contact with us. This material is very useful. Suppose you put in glue inside. If you apply electric field, it can release suddenly. So we can use the active glue. So it's very useful for glue. Another one, you can use a smart elastomer. Smart elastomer, you can use a damping system. Even you can use a train damping system. Use these materials. Okay, so thank you very much. Okay, we are going to show what? Yeah. Yeah. Water. Oh, it's not. Yeah, in the center region, it's become. That's because apply the voltage, his temperature increase. So you can say change a little bit. You use the water. Give water. See? Yeah, it's just like a battery. Yeah.
Can you change it even further?
Yeah, sure. High voltage. We just low voltage.
Okay.
Yeah.
This not lunch normally. I understand that everybody who comes here, time is precious. So we work with a very tight schedule. We try to finish before 2:00. And what we would like here is that's the reason why we have today you come in. It's all very quickly done. Because we really don't want to miss the chance of the professor to show us what he has to say.
Yeah, I will show you this smart window is a timer fast. Hot water. Yeah. Hot water. Yeah. We just change temperature. The half is hot water, half is cool. So you can say half is a Yeah. Put here. It's a hot water. We just show you quickly. Yeah. Okay, so here's hot water. It's temperature. You just put this inside. Very fast. Yeah. So it's changing, instantly. And you put in the hot, cool water. It's changed back again. Oh, sorry. Yeah, it's not true.
Is there any glass manufacturer talking to you about this?
Yes, many manufacturers talk to us in Shenzhen, but we don't want to, give this to them. This is invented by Hong Kong.
Because actually a few years ago, I was trying to put this in my office, except I couldn't afford it because the glass panel was so expensive. So what are you talking now? Because when we're talking about glass panel, it's about $100,000.
We can use glass panels. That's why, because the one guys from hotel. He told us if you come use the bathroom in the hotel, and if you turn on turn on, yeah, and you turn off, it's become transparent. So you can say, and very useful application is a display. So in our lab, we develop a new type of display with this material. Why? Because it's low cost. Very low price.
How low is low?
How low? Like water. That's true. It's like water. Yeah, maybe water is one. Is a. What is it? So suppose it's maybe it's 500. Oh, 5 yuan. Yeah, if like this liquid is 6 yuan. It's very cheap, but it's some secret. Process secret. It's like very cheap. So don't worry about this materials price. You just consider how to design your device. That device maybe is very expensive design.
So if anybody knows if they want to further know something about this or application, then you know who to go to, Dr. Wood. Normally we schedule until about 2 o'clock, and we still have 15 minutes. Anybody would like to have any questions to further clarify this?
A couple of questions, Professor. First of all, if you're going to use it for, say, a window, and you're going to switch between the two states by voltage, you say.
Yeah.
Now, what happened to how is it going to relate to the ambient temperature change? Because your building could be very cold at night and very hot.
Yeah, sure. So you have two double layer. So this material, you have two, types. One we call the passive. Passive not mean without apply the voltage. You just put a roof. The high temperature is just broke.
Yeah, that's because that way it's being controlled by the ambient temperature.
Yeah, true.
I'm thinking that I don't want to be concerned.
Yeah, you can use an electric field. That's why? Because the room in summer is an air conditioner, so the temperature is low, but outside is high. So you have to use two panels.
Okay.
So you can seal outside and inside. The inside just controlled by the electric field.
Right.
So that's easy.
Yeah. The other question, Professor, because everybody's
we've
got a short time, is if we use it for display application, what would be the response time, the switching time between opaque and...
Not like a liquid crystal. It's very slow.
Okay.
Like a.
But advertising sign is okay.
Yeah, that's true. That's true. Advertise.
Yeah.
So it's large panel. Maybe you can flash. Maybe 1 minute is fine.
So I can make it addressable with dots and things like that.
Sure, no problem. We can address. The solution depends on your micro heater. So we actually can make a micro heater. So inside is an ITO. So you can etch ITO like a pixel by pixel. So that's like an LCD panel. It's the same.
Thanks very much.
Yeah.
Gives a chance to other people to ask questions. Thanks very much.
On the drug release,
The drug release.
Oh.
Right. I'm curious because it's very similar to like what they call a time release.
Time release.
Yeah, because certain drugs, because they time the
Okay. That's
is that how it works?
Yes. This is active release. Time release is a drug, the porous materials. And the drug in the pores, it just release depends on your environmental conditions. That's a passive.
Yeah.
You not control the release. But this materials you can apply magnetic field. Apply field, this vibration is hard, so the drug can be released very fast.
So what your own body internal organs is what controls the.
Use an external magnetic field.
Or you have to have an
magnetic field. Use a magnet. You can use a magnet, but this magnet is an ASA magnet. You just apply ASA, vibration.
Okay, so when you do it, do you spray it during the process, or is it just a hard core that you put the medicine in?
Yeah, you can embed the medicine in a core only. So here is a materials.
And that's soluble?
That's soluble, no problem. You have to use you can use any materials. Use a biocompact materials. So you can use what material you used? A PDMS. But it's not PDMS in our knives right now. We can use a catechin. Catechin. So catechin is a biocompatible. You can purchase from any drugstore. Yeah.
Okay, thank you.
You're welcome.
Yeah, thank you, Professor. That was very interesting. Is it possible, I noticed now that the fluid is transparent. Is it possible to add pigments into it to give it color?
That's a good question. We are now developing such materials, but no such material in the world. So we are developing now. So it's a very smart question. Why? Because this material is not color. So if it become color, that's the color display. That's the value. It's much valuable compared to this one. But it's a first generation materials. But I have 3 PhD students, or I have 1 PhD student and 2 postdocs are developing such material like yours. Yeah, it's a color change. It's very difficult. That's because color from color to transparent, it's very difficult. From color to optical is fine. So that's a challenge for us. Maybe next year we can report to you.
We look forward to it. Thank you,
That's
Professor.
true. Thank you.
you.
Thank you very much.
Professor, this is very interesting topic, but I would like to understand more whether there is any side effect to human and also whether this is environmental friendly as far as the liquid is concerned.
Okay, so actually it's for the hairs, it's a materials. You just choose different materials. But this calcium actually is you can dispose in the body. So it's a no. Another one is a magnetic particles is a iron oxide. Iron oxide is useful for the body. It's no problem. Another one, but right now our drug liver materials is only for the stomach. But you cannot use a broad tubers. That's very interesting. Very dangerous because we have no such technicals how to dissolve these materials. So we are trying to do the next step. Yeah, I will report to you later.
Sorry, Professor. I'm also very interested in the glasses, as you have said, it's in the first stage, and I think the application you have mentioned in the bathroom in the hotel maybe more realistic. But even for that, I also have the concern about the response time. For me, I would like to click the button and it can be transparent or fog already. But from your experiment, it can take maybe 1 minute or 2 minutes.
No, don't worry about that. Why? Because bathroom, you go into bathroom, you must turn on your
heat the water. So
yeah, sure. So it's steam. Her steam is rapidly just hitting this window.
Okay, so you use the time to heat the water
to
heat your glass.
1 minute is enough. 1 minute you just you just off your clothes. It goes in. Oh, it's broad. So no problem. Don't worry about that.
Okay,
yeah.
thank you.
5 minutes.
Back to the biological question. My name is Annette Rossi. Can this fluid be injected in areas that are inoperable for cancer?
Yeah, I actually we don't test like inject, but it's possible. That's good. Why? Because this particle is a micron. It's a 50 micron. It's very small. So actually, it's like a small particle. You can inject to, but I'm not sure you can inject to your it's a broad tubers. That's dangerous. I'm not sure. But stomach is fine. It's no problem. But we're trying use some encapsulate with some other medicines to try. It's a real treatment for some disease. We are doing in some institutions. Yeah. But I encourage you, all you can sponsor our research in future. That's because we have knocked out the research funding. So this invention actually invented almost maybe 20 years ago, but we have allowed enough funding.
Well, I think, human beings evolved from Stone Age to Bronze Age, and it was one giant step. And I think, as we're moving towards the Nano Age, it could be another giant step. And maybe by that time, we don't need to be that smart anymore because our materials are doing it all for us.
Oh, yeah. Okay.
But, well, this is, I think, just a scratch of, what the university is doing as a research, and for us to know a little bit about the nanotechnology and smart materials. We have no idea how these things would evolve from here onwards. But I wish to thank you for coming, and I wish to thank the professor for coming also to enlighten us, with this very interesting thing. Because before I came into this room today, the only thing I know about nanotechnologies is it means very small. But to have this kind of new applications.
Yeah.
And I'm sure that, within a decade, 2 or 3 decades, it will become so natural. Yeah. But just thank you very much.
Thank you.
If there's anything that you people want to know more about this, then, please.
Another statement. Today happens to be the launch of a new mini website the Hong Kong UST has, which is called A Good Story to Tell. And you can access it from the general website of the university. And we have little stories about UST, some of which are related to research, some of which are related to any other experience about Hong Kong UST. So if you have time, sometime, click on, and you find some very interesting things. And if you like them, we can have a viral function. You can spread it to your friends. And so today is the launch day.
Well, and then the most important thing is, please do come next time. If you can't, just like some other friends of ours, he sent their friends to come. So today I have met somebody who came because he was recommended by a friend of ours. Who was that? Just now. Nobody want to admit that. Anyway, thank you very much for coming today. Thank you.
All right.